go through this once. So the question is, what is deep learning? And we start with what is artificial intelligence. Artificial intelligence usually is used to refer to machine intelligence, a broader concept that encompasses machine learning and deep learning. And machine learning is a subset of AI, or artificial intelligence, or machine intelligence. And deep learning is a smaller subset of machine intelligence. And you're gonna know about them a little bit down. And there are a lot of, in science fiction and in literature, a lot of speculation about what will happen if the machine intelligence reaches human intelligence or surpasses human intelligence. And actually, I will recommend you to watch Sam Harris talk on this. This is a very interesting one, and compares what will happen if machine intelligence ever reaches human intelligence. So, but deep learning is a subset of machine learning techniques, and what we will talk about in this workshop is just deep learning. So, but why neural networks? Why they are called neural networks? The reason is there is a similarity, kind of a loose similarity between these two. If you have a neural network like this picture over here, so what will happen is that when you have electrical signal in dendrites, so when it reaches the threshold, a signal will be sent through this neuron, and the same principle applies here. In neural networks, you will have an input, and this input will get some weights plus biases, and once it reaches a threshold, it gives an output. So because of this similarity, they are called neural networks, because they mimic neural nets that we have in our brain. But the idea is not new, actually. The idea has been around since 1940. But the question is, if the idea is not new, why it took off recently? Or let's say, more precisely after 2010. There are two reasons for this. Reason one is computational power. Deep learning techniques need a lot of computational power in order to run or to be trained. Plus, you need a lot of data. By data here, we mean labeled data. And Internet of Things, and let's say our use of internet and our devices give us a lot of available data that can be used to train neural networks. These two, hand in hand, helped deep learning techniques to be used quite extensively nowadays. And here's another point, that there's a difference between machine learning and deep learning. While machine learning techniques will saturate at some point with increase of the data, deep learning techniques are always hungry for more data. The more extensive is your network, you can train it and get better performance and result using deep learning techniques. So we have to keep this image in our head. This is the main image we need to think about standard neural networks. But what is a neural network? Let's say I have a neural network with one hidden layer. What it does is that, imagine you have a vector, and this vector input can be anything. For example, you want to calculate the housing price, right? So it could be features of the house, how many rooms it has, the square area, where it's located. So this feature vector will go into the neural net. Now here we have one specific hidden layer, and then it will, the arithmetics will be done, and you're going to get results. Here, for example, there are two, but in the case of housing price, it will be one. How this training happens? It happens through the weights, meaning that you will provide the features, you will provide the output by training or by minimizing what we call loss function. You're going to hear about it soon. The network learns how features are correlated with the output. So this is in general what is called a standard neural network, and that's how it works. there is nothing, I mean, here I should, I mean, yeah, here is the difference between machine learning techniques and deep learning techniques. Machine learning techniques is exactly like this picture with one hidden layer, meaning that you have a model, you have a statistical model, and you want to fit that the statistical model, which has just few or shallow depth, and you do it through fitting or training, and that's called machine learning. But deep learning means you have much deeper networks, meaning you have multi-layers network structure, and you train it, and that's the difference. Well, for machine learning techniques, there are plenty of interesting materials available online. I'm going to skip and not, I mean, I'm not going to talk about what is available. I already talked about how deep learning is done. I mean, the material say the input is shown or fed to the model, and as I mentioned, the output, the correlation between input and output trains the model. So deep learning has been used in many different applications. And this is one application, I mean, that we will also talk about, but not as extensive as you see here. This is a YOLO, the YOLO CNN model, where it detects the object in images. And this is convolutional neural nets, which are specialized for images and videos. And this is one application of deep learning. And as you can see here, for example, your network has many layers and multi-million, perhaps, or hundreds of thousands of parameters to be trained based on the data set you have. And of course, I mean, deep learning is not just about classification of images. It can be about many other things, like playing video games using reinforcement learning, driving cars the same, or machine translation as you have used in Google and many other places, and plenty of other applications. So far, so here you see what sort of problems that deep learning can solve. And I say this list is really not what deep learning can do. I mean, there are plenty of other applications that you can find. Just, for example, have a look at Keras website. In Keras website, you can actually see examples of what deep learning can do with the codes. And as you can see, you have computer vision, you have natural language processing, dealing with structured data, time series analysis, dealing with audio results. If you're interested in generative adversarial networks to create a fake data set or fake result out of your data set, you can see examples here. Reinforcement learning, as I mentioned, many examples here that are available. You can, if you're interested, you can have a look, although some of them might be a little bit advanced and you need a deeper understanding of Keras or TensorFlow. Anyway, so there are many examples of neural networks that you can find, and more you can find in these links. But here is a caveat, and I guess we all know that what deep learning methods cannot solve. Of course, if the data you have is not, if you train the model based on one data set and you're asking a question in a data set which the model hasn't seen, deep learning model cannot pick it up. I mean, that's rational to think. And of course, since it is a very statistical way of learning, why the answer has been arrived, it's not really feasible, although there has been many attempts in this direction to understand what happens to the weights and how one can make use of weights when the network is trained, what this set of weights mean, how one can infer information from parameters at the end of the training. And this is very important. If you have very small amount of training data, it's almost impossible to train deep learning, although you can do augmentation methods. still you need to have sufficient amount of data to train a deep learning model. And well, yeah, I mean, again, here you see what sort of problems can be solved, but shouldn't be used for. Well, I would say this is the way of the author. I take it with a grain of salt. I mean, but some of these, for example, there are softwares for this. You don't need a deep learning to deal with images, or even you have governing equations. You usually don't do that, although there are plenty of applications. I mean, if you in computational physics, people are using deep learning, even though there are governing equations for other purposes. So again, I mean, I personally disagree with this point, but in most cases, this can be true. Now we have some interesting exercise. Let's have a discussion about deep learning together. So, Tor, do you have any suggestions? Should we copy paste this in HackMD, or we should have it?
Well, I was thinking to use the other exercise for typing into HackMD. So this one maybe you can just discuss. There was the other one where everyone, all the participants here, start thinking about how they could use deep learning for their own problems.
Okay, sure. Okay, so I will just skip through this one, although you can think about it. Which of these following tasks you need deep learning for? I mean, even actually we can have a look at this one, and because there's another, because when we talk about deep learning or supervised deep learning, there are several categories. So recognizing whether or not a picture contains a bird, this means a classification task, right? Calculate the median and inter of the data set. Of course, you don't need a deep learning for this. This is arithmetics. And identifying MRI images of a rare disease when only 1 or 2 examples available for training. You can't do that because the training data set is too small. Identifying people in the picture after being trained, impossible, because the network has not been trained to know people in the picture. It knows just cats and dogs. Translation English to French, of course, possible. So yeah, I mean, it's a good idea just thinking about the principle or guidelines given above, what sort of task one can do with deep learning. And the question is, how much data do you need? It's in principle the difficult question to answer. Depends on the depth of the network, but usually, if you have small amount of data, you can't really train a network. And I mean, one can say it really depends on the task at hand. And I mean, well, yeah, when nothing else I can actually add here. So let's go to this bit, the workflow. So imagine now you have a problem and you want to apply deep learning to your problem. What sort of steps you have to go through? I mean, the first step is to formulate the problem. What is the problem you want to solve? And is it a classification? Is it for example, classification of, as we mentioned above, cats and dogs, or it's classification of handwritten characters, or it's some sort of prediction based on time series, or prediction based on some numerical values. Once you know that, then you can decide about what sort of network is useful for you. The next step is to identify inputs and outputs. When you know, when you formulate the task, then you can decide what sort of inputs and outputs you need to have for your model to be. And then this means, I mean, then this step actually takes us to the next step. We are dealing with a network that just knows numbers. So, for example, if you have a text, you need to transfer it to numerical data. or if you have some other feature, you want to do feature engineering. So this is where you do some pre-processing of your input data in order to make it suitable for your network. And once you've gone through this, then you can pick a model either from the library available online, like Keras that I've shown you, or many other libraries. And you can train your model, or you can build your model from scratch. That really depends on amount of data you have and your use case. And here is the loss function and optimizer. So once you have the model, you need to have a loss function. And what is a loss function? If you remember, I talked about an input and output and weight. So how you train a model, you need to have single identifier in order to tell the network whether the prediction is good or not. And that single identifier is the loss function. Loss function tells the difference between the output generated by the model and the output, the true output. This, the difference will be the loss function. And you want to minimize this. And how you minimize it? By minimizing the loss function with respect to weights inside the model. And this actually takes us to the concept of backpropagation that it's not talked about in this document, but you can find plenty of information online about it. So, and every task needs its own loss function. For example, classification needs, the binary classification needs binary cross entropy. If your classes are more than 2, then you need some other loss function like categorical entropy. If your output is numerical, then you might need, for example, some numerical loss functions such as mean risk root squared or some other numerical values. So at the end of the day, you need to have some single identifier to tell the network what you got here is correct, what you got there is not correct. And this loss function must be appropriate with type of the output that you have. And Keras actually provides loss functions that we usually need. And once you have a loss function, the way that you minimize a loss function will be through the gradient descent. And it's done usually using optimizers, different optimizers already developed for you. You just pick one and set the values, or set the, usually the learning rate in order for the network to be trained. Then again, there are a lot of information online about how to choose the optimizer or what sort of optimizer is good for your task. The rule of thumb is that Adam is the most stable one, and I guess we're going to use Adam in most of the examples here, but it's not the only case. You can read about it in Keras or TensorFlow about the other optimizers and how other, not just learning rate, because other optimizers have other parameters to be tuned, and how one can tune that. All of that said, now it's time to train the model. So again, within this course, we just use model.fit API, so you don't need to write your own training loop. But once you train the model, you should see something like this. Your loss function should drop with the number of epoch. So what is epoch? So if you take all of your data and you just pass through your model once, that means 1 epoch. And usually you do it by batching your model, by batching your data. You batch it into smaller subset and you let the network see each batches. And again, how the batching can change the convergence. These are things that you have to find other materials online to know what's really going on. But the general trend must be similar to this. After a few steps of training, you should see gradually your loss function decreases with epochs, with our number of training steps. And that means your network is learning that how to minimize its error. And once we have done that, we usually test whether the model is correct or not. And how we do that, right in the beginning of the preparation of the data, we leave aside small amount of data set for test purposes. And how much depends on how much data do we have. For example, if you have 1 million pictures, usually you need 1% of that. But if you have, let's say, 1,000 pictures, that's a different story. Again, in how to choose this one, it's an art, and MLOps actually is all about this, how to deal with data sets and how to feed it to the model. And we do need to do this because there might be, if you train the model on a specific training data, your model might pick up some features which are not really general, and test data set will tell you that this is the accuracy that you see here is really not real. And so testing is very important. And as we mentioned, yeah, you have to keep track of the performance. Here is loss. You can also add accuracy and other measures to make sure that your model is training in the right direction. And there's another measure that we usually add, and that's validation data set. Now, here there are several ways to do it. So validation data set is a data set that while the model is being trained, you also do the calculations for some other measures such as loss or accuracy. And you check that and compare it with your loss function result. Here you can use either your test data set as your validation, which is the normal procedure these days, or you can, within that model.fit API, you can say, take this fraction of the training data and use it as a validation data set. And the API does that for you. So, and then at the end of the day, once you have trained the model, then you know that what was the performance, what is the accuracy, and the rest. Sometimes you want to just tune the hyperparameters by yourself because you have some idea how to tune it. And well, this is for more advanced users, especially, for example, if you want to do transfer learning. So you want to add a few layers on top of the model you already have. So you freeze the parameters before those layers, and you just train those specific layers you added. Or there are other, examples that you might need to be able. You might need to be able to tune your parameters because you expect specific behavior from your model. And well, sharing your model, that depends on really the privacy and things. I mean, at your organization, you might not be able to share your model, or you might be able. But it's a good idea in general to share your model because the use case with others can help you to find issues with your model or make your model better. Now we have come to deep learning workflow exercise. Before we get to this exercise, I just want to say that these steps are very natural. I mean, naturally, you just, I guess, for any other system or let's say programming, we do this. And the only thing that we need to be careful in deep learning is about choosing the model and choosing the loss function here. But these two will, if we are careful with these two, more or less, we can expect some rational or I would say normal results. Okay, what sort of libraries do we have available? Here, the three are, mentioned, but there are plenty of others libraries. TensorFlow, PyTorch are two famous libraries, and most of the development are usually happening between these two communities. TensorFlow is very, it's very sort of useful among production people, those who use deep learning in production, and PyTorch in research communities. And as it's mentioned here, it has more Pythonic field, while TensorFlow is a little bit different. Keras is an API developed to make the life for people who use TensorFlow easier. And we're going to use Keras throughout this course. And if you need any information about Keras, the website itself, as I've shown here, it's really a good website. You can check this website and find very nice explanation for different functionality of Keras. And in TensorFlow 1, Keras was a different module, but since TensorFlow 2, whenever you install the TensorFlow, you already have Keras installed with it. And it's also mentioned that Keras adds some overhead to communication, meaning that if you use Keras to build a model, train a model, it might take a little bit longer if you do it using native TensorFlow. But it also pays off, considering that you don't need to program a lot. You just need to, to write a few lines of code, and you're ready to go. So let's do two things. If you have a question, please come forward, ask your question, or if you want to discuss about something, let's do that first, and then we can have this exercise before we spin up our Jupyter notebooks and check whether we have available libraries for the next session.
Okay. So there was one question that I wanted to ask you, Hossein.
Yeah, sure, yeah.
How are trained models, so this came up in HackMD, how are trained models stored and shared? Is there a standard file format?
Good question. Yes, depending on the library you use. For example, if you use TensorFlow, there are, for example, HDF5, we can use that. But there are, depending on the library, there are ways to save it. And in PyTorch, in TensorFlow, we use callbacks to save the model. And it's saved in a standard form, but you can save and load it somewhere else. So the answer is yes.
So since I haven't, the different libraries.
Yes, yeah. Since I haven't used PyTorch, I can't really comment on that. But on TensorFlow, I've used, and actually I've done it myself. And in transfer learning, this is a very, very standard thing to do, And let me see. Yeah, well, I can actually find the GitHub of TensorFlow, official GitHub, and can show you how the saved model look like. You can see how the parameters are saved. But there are standards within the library. The short answer is this.
Okay. Any questions that anyone wants to bring up by voice for a discussion? Otherwise, we have a task for you to do in HackMD. So I just added again the link to our HackMD document to the Zoom chat. So we're using this document to ask questions and answer questions. Asking by voice is perfect, but you can also write questions down, and they will get an answer in written form. Shall we talk about the exercise?
Yes.
It's not a heavy exercise for you to do. It's a question of thinking about your problem. So in HackMD at the bottom, maybe could you scroll down in HackMD? Do you have it?
Yes, I have it. Let me bring it here in my browser. Now you should be able. Yes.
Yeah. So what do you want a deep learning system to be able to tell you? What data inputs and outputs will you have? Do you think you'll need to train the network from scratch, or will a pre-trained network be suitable? What data do you have to train with? What preparation will your data need? We're not asking for an essay, but think about these for your particular use case. And if you like, write something down in HackMD so we can discuss it, or I'm not forcing you to do it, but you can edit if you scroll down a little bit. You can write something under the bullet points there below the box.
And if you need breakout rooms to discuss with your peers, we can actually open breakout rooms if you think that's easier. Otherwise, we can use HackMD.
So I think it's very interesting to see your use cases that you have in mind. Some of you are probably already started doing this, but many of these are probably ideas, and they look very like very good use cases. And it's fascinating, to see all these different scientific domains, all these problems, scientific engineering problems, everyone having a common interest in using deep learning to tackle them. I think the purpose of you writing things down here is to, if you haven't done it much before, is to get you to think about these problems, based on Hosein's presentation, to formulate the problem properly, to identify what inputs and outputs you need to have or you want to have, whether you can reuse existing networks, what data you have, what preparation is needed. So all these questions are very important to have an idea of in your mind before you get started. So I think we can be happy with this. Keep writing if you want, but I think it's definitely time for a break.
Well, yeah, you're right. But before we go for a break,
yeah,
please spin up your Jupyter notebooks.
Right. Yeah, of course. We have
and then check whether you need to have TensorFlow, Keras, Seaborn, and scikit-learn modules available for your next task, next episode. Let's just make sure you have all of those available before we go for a break. And if you can't run it, you can share with us your issue and we try to solve it here.
Yeah. So everyone is supposed to open up Jupyter now. So you can run Jupyter Lab or Jupyter Notebook. Either one is fine. And there are these exercises at the bottom of that page that you see on Hosein's screen.
Yep. Copy
Paste these lines of code and run them to see that they should give you versions. And if they don't, tell us about it. So write in HackMD or write in the Zoom chat or a private message to me or Hosein, and we can try and troubleshoot in a breakout room. So let's take a couple of more minutes for you to do this, to open up Jupyter. If you've never used Jupyter before, how you started, I guess, will depend on your operating system. So on Linux and Mac, I think you just write Jupyter Lab or Jupyter Notebook with a dash, minus sign in between in your terminal. While I think most Windows users go via the Anaconda Navigator, I think. So you open up the Anaconda Navigator and you find Jupyter there, and you just click the icon for Jupyter. But please let us know of any problems.
And if you have issues running Jupyter locally, you can always use Google Colab, which is free. And all you need to have is to have a Google account.
Yeah. So that's a fallback option. If something is not working for you and it's not an obvious problem that can be solved easily, you can use Google Colab.
Yeah.
And I will share a link to the installation instructions again that I sent you via email earlier. I just copy pasted into the Zoom chat. So at the bottom of that page, you can find information about using Google Colab. Okay, I hope we're ready to start.
Just one short comment. I saw at HackMD that someone asked, please explain hyperparameters again. So I feel like this must be clarified, because maybe slip of tongue. What I wanted to say is that once a model was set up by someone, and that person used some hyperparameter, and you want to do transfer learning, you can tune it in the way you like. And as it mentioned, their hyperparameters are the parameters that you as a user define to set up the model. And it can be learning rate and other parameters too. It's just simple clarification.
Good. So again, you can keep the questions coming in HackMD at the very bottom. Just scroll all the way down so we don't miss any questions. It's my turn now to share my screen again. And it's still being recorded, yeah. So I will leave answering questions to others now and focus myself on teaching. So back to the lesson. I now have two windows side by side. I hope this will be okay for you. I know it can be difficult with screen space sometimes. You want to see what I'm showing you in Jupyter and the lesson itself, but then you want to have your own window with the Jupyter Lab or the Jupyter Notebook. I know this is a challenge. I hope you can work it out somehow. To resize the windows on your screen so you can multitask. You can type. You can follow what I'm saying. But please let me know of any problems if font size is too small or anything like that. So I will go into the second episode here, classification by a neural network using Keras. Maybe I'll make the window a little bit larger. So we'll really go through the full workflow here that Hossein talked about, steps 1 to 10. And along the way, we'll get a glimpse of what neural networks are and how one specifically uses Keras to construct them, to use them, to test them. We will work on a data set, we'll see how to train a network on a data set, how to get insights into the learning process, how the loss goes down and so on, and how we finally test the performance of a network. So here's a reminder of the steps we just saw. So first we formulate, outline the problem, identify inputs, outputs, prepare the data, choose a pre-trained model or starting building the network architecture from scratch. We choose these hyperparameters, if you will. So we choose a loss function, we choose an optimizer, we then train, we then test it, we try making a prediction or a classification, we then more rigorously somehow measure the performance, and then we can go on and tune hyperparameters, and finally we can save the model for later purposes and to share it with others. So we will be working on a small data set, which still is amenable to machine learning, to deep learning. So let's formulate the problem. We will be classifying penguins. It didn't look like any of you was working on penguin classification, so hopefully this is something new for all of you. It's a nice data set published quite recently by Alison Horst. Contains data on 3 different species of penguins. And the goal that we specify already at the outset is we want to predict a penguin species using the attributes available in the dataset. So there are 3 species, chinstrap, Gentoo, Adelie penguins. They are found somewhere in the Antarctic, and the data was collected by someone here between the years of 2007 and 2009. Okay, so that was the first step. We know what the problem is. We know what the data set is. Let's go on and identify inputs and outputs and have a look at the data set in more detail. I will now multitask and open up a new notebook. And I will follow good practice and I will save this notebook. I don't want it to be called untitled.ipynb, so let's save it as and please interrupt if you have any issues, technical issues. I will now start typing or copy pasting sometimes, and you should be typing along most of the time. Maybe it goes slightly too fast for type along sometimes, but there will hopefully always be time for you to catch up. So let's download the dataset. And for that purpose, we first load the Seaborn library in Python, because the dataset itself is available in Seaborn. Seaborn is a plotting library, but it also has several datasets pre-defined in the library. So if anyone is unused to Jupyter, you write code into these cells here. You get a first cell initially, and then you write your code there, and then you can either press the play button at the top. This might look slightly different if you're in a Jupyter Notebook. So this is a Jupyter Lab instance here, but there will still be a play button somewhere at the top, or you can press Shift Enter, and it runs the cell. And you can see here on the left that there's a number. That's because I've run this cell twice now. So this is in order to keep track of in which order the cells have been executed. I'll just copy paste this line here. What's happening here? We want to load into a variable penguins, the data set called penguins. So Shift Enter. Okay, there's no error, something got loaded. Let's do this one together. What are the different features called? What does the data set contain? I could just write penguins, Shift Enter. So, you know, if you just put a variable here in a Jupyter Notebook, it prints it. You don't have to use the print explicitly. So what do we see? I will actually do it differently. I will do a penguins.head. This only prints the first 5 rows. I can put the 10 here to print the first 10 rows. We have a column for the species. This will be our target. This is what we will want to predict later on. We have the island the penguin was found on, and then some physical features of the penguin. So the length of the bill, the beak, the depth of it, flipper length, body mass, and then the gender of the penguin. How many samples does this data set have? One way to find out is to use this very convenient overview function called describe. First, I want to tell you one thing. So what is penguins? First, I'll teach you one Jupyter trick. I want to insert a new code cell above this code cell here. How do I do that? So first, I go to edit mode. No, sorry, I go to what's it called now? Command mode. So I press the escape key. Escape, because now I'm in edit mode. I can write into the cell. To go back to command mode, I press the escape key, and it sort of gets deactivated now. I could probably go in somewhere here and add a new cell, but I want to do it more easy. I press the A button, A key. Now, I got a new code cell. I just wanted to show you the type. What type is this penguins variable? It's a data frame. Many of you might be familiar with data frames. They are very convenient structure type in Python, available in the data frames, pandas library. And it's really the data frames which allow us to get such a nice visual representation of the data with columns and rows, and then also to get the overview statistics here using the describe function. So what this shows us is statistical values for the data set. So we get the number of values. We have 342 rows of measurements for all these different columns here. And we can see the mean value, we can see the standard deviation, the minimum, maximum, and different percentiles in between. So is there something here in the solution that we missed? We have the head function, the describe function. This is maybe interesting. We can select a column of the data frame. We select the species column, and then we use the unique function on that. So what happens? Shift Enter. It tells me what are the unique entries in the species column. These are the 3 types of penguins. We can actually count them. penguins, species describe. We didn't get any statistics here in the initial call to describe. We only got results for the numerical columns. But if we call this explicitly on this species column, which has string values, or what is it here, string values, we actually get a count. We see that there are, so 344 values, unique, 3 unique, the most common value is Adelie. Okay, let us visualize the data. This is always very useful to do, obviously, to get an idea of what you have in the data set. And let's use the pair plot high-level plotting function here from the Seaborn library. So it's really amazing. You can just call this single line of code. You pass in the penguins data frame, and then you choose which hue. So how do you want to group the data in your plot? And we run this and get this very nice looking, it's called a pair plot. And so it automatically generates 16 plots, 4 by 4, with correlations between the features. So body mass versus bill length, body mass versus bill depth, and so on. And on the diagonal, we have density plots. And they're all colored by the species of the penguin, because that's what we selected here. So there's a question now. Let's have a look at the pair plot. Is there any class which is easily distinguishable from the others? Any class of penguins? Do we expect any of the penguin species to be more easily predicted by our network later on? And which combination of attributes shows the best separation for all 3 class labels at once? Let's have a look at this. I know this is a bit small, but I would say that maybe the Gentoo species might be most easily distinguishable from the others. So you see, for example, here the combination of flipper length and bill depth. The green blob here is quite cleanly separated from the rest. So Gentoo is might be easiest for the neural network to predict later on. And which combination of features, if we look at this here, bill length versus bill depth versus bill length, we see that there is, the species can be told apart pretty well here. Maybe this is a good combination of features too. While something like here, it's impossible to tell apart. If you combine flipper length and bill depth, it's impossible to tell apart Adelie and chinstrap penguins. Okay, input-output selection. We have loaded the data set into a data frame. Let's decide what to do here. We make a selection. What features do we want to use? As features for the training, we choose to use the bill length in millimeters, bill depth, flipper length, body mass, all of these 4. So we will skip what we saw before. We will not use the island the penguin is found on, and not the sex of the penguin. All the numerical values here. We now need to prepare the data. This is always the case with machine learning. You have the data set, but you need to clean it up. You need to pre-process it in several ways, usually. So the data is not already in a format that's suitable. So one thing we do to make this, to make it easier to work with, because we will use the species column. And currently, I think you saw this up here somewhere. I'm not sure, but so the species column has these different strings, and the D type is object. We want the D type, the type of this column to be different. We want it to be a categorical type. Categorical type is something you implemented in the pandas data frames package. So this is just for later purposes. We override the species column. We override it with the same column, but cast to a category type. This will simply make the interaction with this column later on easier. Another thing we might have seen in the listing of the values, if we looked at the first 10 rows here, is that some of the values, some of the rows have missing values. This will be a problem. We cannot really use rows of the data set which have missing values. So NaN, not a number. There are different ways generally to deal with this. It depends on the problem, what type of problem you have. Sometimes some fake data is used instead, or interpolation, if it's a time series data set. In many cases, the best thing to do is simply to drop the columns which have missing values. So there are two things we do here in this code cell. We create a new data frame called Penguins Filtered, where we drop first the two columns we will not use, the island and sex columns, and then we drop the not a number rows. And finally, we extract only the features from that filter data frame by dropping the species, because we will have the species separately. Let me just copy paste. Look, penguins filtered dot head. This is now a smaller data frame. We remove the columns. I can do the same thing for the penguins features. Now the species column is gone. So penguins features contains our training data. We also have to prepare the target data. These are often called the labels that we want to use to teach our network to identify penguins, right? Target data, or the labels that we have. And we made it into a categorical type, but that's still not a useful format. So the neural network can only take numerical inputs and outputs, like we saw in the last episode. And it learns by calculating somehow how far away the predicted species is from the true species. And this will not work with a column which has these categories. So there needs to be some way of calculating a distance or an error. So what we do specifically is to use what's called one-hot encoding. There are other ways to do this, but I think one-hot encoding is the most common way. And we have a method in the pandas library, the getDummies function. I don't know why it's called this. So we import pandas, we name it as PD, and then we extract the species column and pass it onto this getDummies function. So let's see what happens if we do this. Execute the cell. Okay, so maybe I just compare this to what we had before. Penguins filtered species. I can also extract a column by using the dot notation. We had this a long array with the values here, Adeli, Gentoo, and so on. If we pass it to this getDummies function, we get instead a matrix with ones and zeros. So the first 5 rows are all Adeli penguins and so on. So this is a numerical type, and it can be used to calculate the loss later on. Okay, next step is to split the data into training and test sets. This was mentioned previously by Hossein. We always need to take out a part of our data set for testing. Otherwise, we have no idea how the model will actually perform in the wild after you train it. So this is standard machine learning. You split into training and test sets. So the training set will be used to train the network, and the test set is kept separate for later testing. We don't need to do this manually ourselves. There are inbuilt functions in scikit-learn and probably other libraries too. This one is very convenient. It's called train test split. We imported here from scikit sklearn dot model selection. We import this function here. And here's the function. What do we pass into it? We pass into it the features that we have and the target. Those are the two first input arguments. We specify the test size. So 20% of the data set should be in the test set. And then we initialize a random seed. And this is to make it reproducible. If you don't specify, there will be a unique split into the training and test sets every time we run this. But I'm not sure we will all get the same numerical data later on. It might depend on version numbers of libraries and so on. But we use the same random seed just in case and see if we get something similar. We also want to shuffle. This is actually quite important because as we see, the list of species in the, well, we can see it here in the one hot encoding, they're all basically ordered. So first are all the Adelie penguins, then the chinstrap. So it would make no sense to split the data in this ordered form. So we have to shuffle the observations. And then here's a sort of more complicated keyword argument, stratify. This is a method. We give it the target value here. This is a method to make sure that the training and test sets are balanced with respect to the populations of the categories here. So we will have as good as possible a distribution of the species in both the test and the target, the test and the training set. So I copy paste, Shift Enter. Let's now explore. I will leave you to do this yourself for a couple of minutes. So we have defined, there were 4 different output variables coming from the train test split function: xtrain, xtest, ytrain, ytest. So please play around. How many samples do the training and test sets have? Are the classes in the training set well balanced? So explore this. I will do it myself. Maybe you need to catch up with some of the typing. So we have a few minutes now. Okay. Yeah.
There's a question, HackMD. Why? I mean, could you please repeat what Panda Get Dummies does?
Yeah, good question. So let's look at the test docstring, not the test string, the docstring. So a very convenient feature in the Jupyter Notebooks is that you can write the name of a function that exists in your namespace. So it comes from the pandas package. We just put a question mark at the end and we execute it. So here's the call signature. These are the different arguments it can take. docstring convert categorical variable. This is why we converted earlier to a categorical variable into a dummy / indicator variable. I don't know why it's called. Actually, Hossein, do you know? I don't know why it's called dummy variable. But this is the one hot encoding that we actually need. So there are some examples here. You have a series object here with ABCA. You call it with the getDummies function. It returns this type of structure. So the first observation is an A. The second one is a B. The third one is a C. And the fourth one is an A. I hope that answers the question. I will, a pro tip for Jupyter, if you didn't know, we can collapse the code cells by pressing right here. I click on the left side and you collapse the output because it's too big. I don't want to see it anymore. Actually, what I could do is to delete the cell, either going to edit, delete somewhere, or just pressing D key twice, ED. ED, now it's gone. Okay, keep the questions coming. I leave it to Hossein to update HackMD. So I want to do, yes, we were talking about the training and the test data. I want to use the shape attribute, for example. So we see here that the training set has 273 rows, observations. The test set has 69. So that's roughly 20%, I guess, of the total. We can use the sum function here to check how many of each species we have in the training set. And the same thing for the test set. And we see that they're roughly balanced. So we have in total the least amount of observation for the chinstrap penguin, but at least this looks as balanced as it could be. Okay, so let's discuss Keras now. That's what we will be using throughout. What is Keras? Hossein mentioned it's a part of TensorFlow. So we import it from TensorFlow. And it's a high-level API. So application programming interface. It exposes many functions and methods to the user, which hides away many of the technical details. We can use a high-level interface, high-level function calls, and don't need to specify every single parameter. So there are functions, classes, and definitions to define deep learning models, cost functions, and optimizers also. So before moving on to the next step, we will import Keras here. And another thing, I mentioned the random seeds before. Let's all put the same random seed. So we have to inject a random seed into the numpy.random module and into the tensorflow.random. We don't need to. We wouldn't want to do this when we are training for production later on, but this is for reproducibility. I'm not sure we will all get identical results, but we might. Some of us might, at least, if we have compatible versions here. So we set these random seeds. Okay. So step 4, we're now here. Should we use a pre-trained model or should we start building a neural network architecture from scratch? What would you think? Well, classifying penguins maybe hasn't been done before. This is our own research project. Let's pretend. So we don't have a neural network model which accepts these features of the physical bodies of penguins. So we start from scratch in this time for this case. This might sound like a daunting task doing it from scratch, but Keras really enables us to do this in a very high level way. So we start by defining the input layer. We saw this. I will go back just to have it open. I will go back to the visualization in the introduction. Scroll down here. The input layer. The input layer should have as many neurons or nodes as we have features. So here we define a layer. So it's a keras.input layer, and the shape should be the shape of the training set. The training set. Let me just print this variable. It's a 4 because we have 4 features. So we're now defining the model. We're defining the first layer. This is the input layer. And we now define the hidden layer. So we will actually be using this architecture. So we have an input layer, a hidden layer, and finally the output layer. Only one hidden layer. And we choose randomly maybe, or by guess from the beginning, to have 10 neurons. We don't have a lot of data. It was in the hundreds. So it's not a lot of data. So we cannot have a too big neural network, and let's try the 10 neurons. That's the first argument, 10, number of neurons. Second argument is which activation function to use. ReLU, the rectified linear unit, is the standard choice. There are other options, but I think it was mentioned earlier, ReLU is the most commonly chosen activation function because it's stable and has good properties. So this function call is a bit funny. So this is the function, keras layers dense, with some input arguments, but then there's another pair of brackets. Funny syntax. I think what this results, what the first part results in here is, I don't know why I cannot. This results in some type of functor, which can be called as a function. So what we actually do is to pass the input layer as an argument to the dense layer. That's just how it works. So we accept it and move on. There's a warning. The binary, TensorFlow binary installed on my machine, I'm not sure you will see the same thing. It's optimized for a particular framework. It's telling me which architectures, which CPU instruction sets it's been optimized for. Never mind that. Let's go now to the last layer, output layer. It looks similar to before. We have a dense layer again. And I don't remember exactly what we talked about in the introduction here, but what does dense mean? Dense layers are also called fully connected layers. It simply means that each neuron is connected to all neurons in the layer preceding it and all neurons in the layer what comes after preceding subsequent layer. So this is a fully connected or dense network, and the hidden layer is dense and the final layer is dense too. So it's connected to all the nodes of the hidden layer in between. Okay, we've defined these 3 layers now, and we can now build the model. So here is another function, keras.model. We tell it what the inputs are and then the outputs. And you see that the output layer has the hidden layer built into it here, right? Same syntax as we saw before. So this is actually the only thing we need. We combine all the layers, and we can print a summary of a constructed network with a summary function. So I will just give you a minute to catch up if you need. So a question to you, how many parameters does the resulting model have? What happens to the number of parameters if we increase or decrease the number of neurons in the hidden layer? So this summary function tells us everything there is to know. So we see that there are 50 parameters in the hidden layer. What's the reason for 50? Why is it 50? So we had 10 neurons. So the reason is that we have weights and biases. I think, is there inputs? But we haven't really talked about the bias, I think. I think we come back to this discussion in a second. But anyway, we see that there are 83 parameters in total.
You can see it in the other graph in the document. And above. There it gives a bias. And
yeah, here's the bias. Yeah, thank you. So every neuron has both a weight and a bias. Anyway, let's move on. So if we would increase the number of neurons in the hidden layer, it would increase the number of parameters here. I'm not going to do it because I would need to re-execute lots of cells, but you should play around with this later. So how did we choose this architecture, or how should one choose an architecture in general? So one has to make a choice on the number of neurons and the number of layers and the types of layers. We'll see more types than later on. Now we've just encountered the dense type. So how do we make these choices? The answer is, unfortunately, that there are no clear rules, and it often boils down to trial and error and eventually to some sort of intuition, I guess. I think machine learning practitioners develop an intuition for what will work, what will not work for particular types of problems. But one can also look at what others have done with similar data sets or similar problems. And another recommendation is to start simple, something small, and then gradually increase the complexity of the model. And as also was mentioned before, if the data or your problem is very similar to what has been done before, one can use a pre-trained network. Even if the problem is different, but the data type is common, for example, images, one can use a pre-trained network and just add a final layer, actually, and train the final layer to work for your particular data set. Okay, it's time for the next step. So we go into the technical details and we pick a loss function and we pick an optimizer. The model is ready, but we need these extra things. We need the loss function and an optimizer. So for this particular encoding that we use, the one-hot encoding, a fitting loss function is the categorical cross entropy, which is implemented in the keras.losses class as the categorical cross entropy class. There are many options, but this is good for these classification problems with categories. So I didn't mention softmax. So in the output layer, let me just show you. So when we specified the output layer here, we specified what the activation should be. In the previous layers, we chose the ReLU. But for the final layer, we chose softmax. Softmax is a way to convert, if I maybe go back here, convert the activations that come from the hidden layer into numbers between 0 and 1. So we will have 3 output neurons, 1 for each type of penguin. And the softmax activation here at the end ensures that what we get for these 3 neurons are numbers between 0 and 1, which can loosely be interpreted as some sort of probability. So if the value of the Adelie neuron turns out to be 0.9 and then 0.1 for the other and 0.0 for the third, that would be a classification of the Adelie species. So that's what the softmax activation function does. And the categorical cross entropy method works for the softmax activation function. And there is a link to the documentation for more information on loss functions. We also need to choose the optimizer, and we don't have to, but we can tune or we can select parameters of the optimizer as well. but these have default values and we will not specify them here. It was already mentioned earlier that the Adam optimizer is a good one. It's well tested, it has good properties, and that's what we'll use here. So the default values of the Adam optimizer work well for most problems. So these parameters are types of hyperparameters, something you can tune. You don't need to tune it, but you can tune it and see if it gives you better performance. This is how we now specify. So we use actually the compile function for the model. And this is where it takes arguments here for the optimizer, which we set to Adam, and the loss, which we set to the categorical cross entropy. Copy paste. Takes a while to compile the model. It's running. No, it's not running. I don't know. It's already run. We are now finally ready to train the model. How do we do that? We use the fit function. So I told you this was a high-level interface to machine learning libraries, to TensorFlow. So there's really not that much detail we need to specify. So we can simply, there are these very convenient high-level functions. And one of the arguments to fit is the number of epochs that we want to run. So that's the number of loops we want to perform over the entire training set. And you see that we specify the features, the training features, and the training labels for the target observations here. And we actually capture something. So this function will return the history. And we will see in a minute how we can plot things from the history. Let's just run it. Okay, nice. It's running. We told it to run 100 epochs, and it took no time at all. It was very fast. And what does it print? It prints the loss, right? You can see here on the right that the loss drops from a big number, almost 3,000, to around 1.5. Let me just minimize this. I'll click here. Okay, so clearly something was happening. What we can do, I told you about the history here. We can use the Seaborn plotting library to plot the epoch attribute here of the history on the x-axis. So to have epochs on the x-axis, and on the y-axis we want the loss, which is captured in the history. Perfect. This is roughly how the plot looked that Hossein showed you an hour ago. The loss should drop quickly, and then, yeah, if everything works fine, it drops quickly in the beginning, and then maybe it flattens out at the end. And of course, it's important to diagnose, to observe this, to have a look, to see that any possible problems could be manifested here. There's no noise we see. We'll see examples later of something that looks more noisy. Do we think that the resulting trained network will work well on the test set? So we trained it on the training set. We really can't tell. I mean, we see that it's really learned a lot about classifying about the penguins in the training set, but that really doesn't say all that much about what the performance would be on the test set. So let's look at that. For that purpose, we use the predict function of the model. So we can define a new variable y prediction, which takes in the test set now and makes a prediction using the trained model. So this model object here contains the, it's been updated with, after the training, it has updated weights, updated biases, all the knobs have been tuned inside the model, and we are ready to make a prediction. And we then make it into a data frame because it looks nicer in the Jupyter Notebook. So what happens? I told you about the softmax function. It converts whatever comes in from the next to final layer and maps it onto numbers between 0 and 1. And we see that the network seems to be quite confident here. So it's really confident that the first sample from the test set is an Adelie penguin. The second one also. The third one should be a it should be a Gentoo penguin, and so on. So this is the output of the trained network. And they can loosely be interpreted as probabilities, but it's not really an exact mapping to that concept. I think we'll soon wrap up this part. There are a few things left, but then we go for a break, I promise. We made some predictions. We want to convert these numbers between 0 and 1 back to classifications of the penguins. And there's this convenient function here called IDX index max, where we convert back to the species categories using the columns. So it's, seeing is easier than explaining. Copy paste it. So this is what we get. It takes the values here, finds the column in which has the largest number, and picks that as the actual value. This we want to compare now to the truth. These are the predicted species. We want to compare them to the actual species, the labels that we have. And that's where we come to the next part, measuring performance more rigorously. We saw that it works. We can make predictions, but let's get an idea, more detailed idea about how correct our model is or how wrong it is. A standard way to visualize these, the accuracy of a model when it comes to classification is the confusion matrix, at least if you have a manageable amount of labels. We have only 3. And this is implemented already in scikit-learn under the metrics class. We extract the true species from the ID test. So remember, the ID test is one hot encoded with 1s and 0s. So we also need to apply the index max function on that one. And then we make a matrix, confusion matrix with the true species, which will also be a list of Adelie, Gentoo, Chinstrap versus the predicted species, and see what it gives us. All right, so this is not very easily interpreted. We know that things should be on the diagonal. Let's plot it in a nicer way using a seaborne heat map. So we make it into data frames. Seaborne works with data frames. This is basically just, we make the data frame and then we name the indexes and the columns. This is just for aesthetic purposes. Finally, we can create the heat map using the annotation argument, set it to true so that we get numbers inside the heat map. This is how it looks for me. Maybe it might be interesting to hear other observations, so particularly where you saw the completely different results. So we have on the x-axis predicted label, and on the y-axis the true one. So in 16 cases, a true label of Adelie is correctly predicted to be Adelie. So if all the numbers would be on the diagonal, it would give a perfect classification, correct in every case. But there are clearly some confusing, the network is clearly confused. So 12 of the Gentoo observations are classified as Adelie. 14 of the Adelie penguins are classified as chinstrap, and so on. I will now wrap up. So we will not tune hyperparameters now. We will do it in the next part. So that would be the next step. We look at, can we improve the model? Is this good enough, or do we need it to perform better? How can we make it perform better? We'll look at that later. But I'll tell you how you can share a model, how you can, well, first of all, save it and then share it. So there's the model.save function. And this comes back to the question that was asked earlier. I'm actually not sure what format it will be in. I can maybe make a new terminal here. It saves things under my first model. It's a PB file. Actually, I don't know this, so we can talk about it later maybe. Anyway, this saves the model. And later, if we wanted to come back to this, we go home from work and we want to keep working on it the morning after, we just load it into memory using the pre-trained, using the load model function. And then we use it to predict or do whatever we want. Okay, everything look fine? Yeah, hope so.
Yes, it is.
Thank you. Let me first now in Jupyter create a new notebook. So I am in Jupyter Lab. For me, I do it this way. I click what's happening, File, New Launcher, and I pick my Python environment that I want to use. And I get a new notebook. If you're running the traditional Jupyter notebook, what do you do then? I guess you do something similar, File, New Notebook. Save it as weather prediction. So it's the same deal now. I will be talking, I will be copy pasting, describing what's happening, and you can do the same. You should type along. You can also, if you want, just watch and listen and type along later or follow the steps later. All the steps are here. So we're now in this part, monitor the training process. This will be a long one. We'll go into some more details than what we have done so far. It's going to be a bit repetitive because we go through the same steps, but it's a different type of problem. We'll go into some more details. So hopefully that's going to be interesting. It's a regression problem rather than a classification problem. We will not finish it today. We will finish it tomorrow. So I'll try to set a good breaking point somewhere, a natural way to conclude the day, and then we pick it up again tomorrow. So monitor the training progress or process. We will see new ways of monitoring the training process, and we will detect overfitting and see how we can tackle that problem. And then we'll also discuss a few options to improve performances of models. So it's a different data set. It's maybe you've already downloaded it. It was part of the setup instructions, but we can also download it with one line of Python in a minute. It's a data set with weather observations from multiple European cities. So if you already have your data set available, you've already downloaded it, you can copy paste this cell, but I will actually do it this way. So you can download data sets, download data from the internet using pandas, using the read CSV function, specifying a path online where the data is living. So first thing to do is to import pandas as PD. And then I'll just copy paste the cell here. So we're in the first step. We're exploring the data. Data.head shows us the first part of our data frame. So we have dates. They are clearly sequentially ordered. 1st of January 2000, 2nd of January 2000, and so on. Month. And then these weather observations. So the cloud cover, that seems to be an integer. Humidity, number. Pressure, global radiation, precipitation, sunshine. The mean temperature, minimum temperature, and so on. Many, many columns for these different cities. Basel, Sandvik, Tours, several cities. We can print all the columns using the columns attribute of the data frame. I forgot an S. Here we get the complete listing. I think Stockholm is in here. No, it isn't. Stockholm is in the full data set. This is a reduced version of the full data set. So let's get a further overview of the data set. So we know now roughly what it contains. It contains these weather observations. How many lines, how many observations? We can have a look at the shape. So 91 columns, quite a few, and these are the number of rows, 3,654. And that corresponds roughly to 10 years of observation. So each observation is on a unique row in the data frame. And each observation is for 1 day. So this is roughly 10 years. Okay, so let's now think about what we can do with this data. So you could do many things with the data. And of course, this is a serious research problem, trying to predict weather using neural networks instead of these large weather simulation codes. It's a difficult problem. And let's see how far we get. So what we will do is to limit ourselves to the first 3 years to begin with. You can play around with this later. We'll select the first 3 years only. And we find an interesting prediction we can make. So we want to predict the weather sometime in the future, say the next day. And because the observations are sorted by date, what we can do is to extract rows. We can have the target be all the rows below. So the target can be sort of shifted 1 row down, if you know what I mean. So maybe the code will be clearer. Here we select the number of rows we want to extract. And here we slice the data frame. We drop these 2 columns, date and month. They, let's say, will not be interesting for training a neural network. We only want the raw data from the weather stations. And then that's for these are the features that we will use. The labels, the target data, will be the Basel sunshine hours. So let's try to predict the number of sunshine hours in the city of Basel. And you see that we slice the data frame differently. We go from 1 to the number of rows plus 1. So this will be shifted in time by 1 day compared to the features. Right? So that's the problem definition. We will try to predict the number of sunshine hours tomorrow in Basel based on weather observations. As we saw before, one often needs to prepare data. There will be, maybe we haven't really done that so far, but often data is in different formats. It's in messy formats. It's collected and it's split over many different locations. One needs to pre-process, one needs to aggregate data from many sources maybe, and clean it up. There might be nonsensical rows with wrong numbers in it, or there could be missing numbers, things like that. And normally we can use now the data describe function. Let me just collapse this here. Data.describe. This would show you, I think, if there were some missing values. You could see the count. But now we see all the columns have equally many values. So this is already a tidy and clean data set. Because we did this before, we did the exact same thing. We used the train test split function to split. I will just do this. Don't have to spend too much time on it. So in this case, it's a little bit different though. We already mentioned splitting a data set not into 2 parts, training and test, but into 3, adding also a validation set. And the validation set is sometimes used to observe the progress of training during the training. And that's what we'll do here. And then afterwards, the test set is used to, as we did before, to compute the performance and compare it. So we have the trained network and we test it on the test set. But the validation set will be there for observing the progress. And if we want to split into these 3 sets, we simply do a trick. We first split into X train and X holdout with a fraction of 0.3. So 70% of the full data set will be our training data. 30% will be split again into a validation set and a test set. So here we split evenly. So 15% will be in the validation set and 15% in the test set. We simply apply the function twice. Copy paste. Now it should work. And then there was a second split. There is one important difference from before. Yes, well, never mind. Yeah, we set the random state to 0 like before. But normally maybe you would not fix it. You would want a more randomness. So, but here we fix a random seed just like we did before. This exercise is not very interesting. It's just sort of a mathematical question. How would you split differently into the training, test, and the validation? Let's skip over that. Okay, let's go right into building our model. But we first observe that what are we predicting? We are predicting the number of sunshine hours. So this is not a category like we had before. This is not a classification task, it's a regression task. We're trying to predict a floating point number, basically. How many hours of sunshine will there be tomorrow in Basel, depending on the weather observations today? So we used the categorical cross entropy before for the loss. This is not relevant anymore if we're trying to do regression. What do we do instead? We use a something that quantifies deviations in a number simply. And a common choice is to use a something like root mean squared error. We'll come back to that. Let's have a look at the model that we want to build. Again, we will use dense layers only. We will see more types of layers later. We will have much larger layers. We have much more data. Hopefully we can get good predictions by having 2 hidden layers instead of 1, and by significantly more neurons than we had before. One difference from before is that we put this into a function, simply because it can be convenient to be able to call this create NN function over and over again if we want to create a new model. from scratch with new random initial guesses for all the weights and so on. There's the same type of chaining going on. We define the input layer, we pass the input layer into the next hidden layer. In turn, we pass that one into the next hidden layer, value activation functions once more. And finally, we add the output layer here and combine them all in the same way as we did before. We can even give it a number, give it a name, weather prediction model. Anyway, I create the model. It gives me the same information here about what the TensorFlow binary has been optimized for. Yes, so one difference from before is that you see how many neurons do we have here at the end? We have one single neuron. And that's just because we're predicting a single value, the number of sunshine hours. So all this complexity inside, but a single value comes out. Yeah. So let's have a look at the summary like we did before. Model.summary. It's a big model, 14, significantly bigger than before. Surprisingly surprisingly to me, the first time I tried it, it's still not too big for my laptop. I can still run it easily. 14,101 parameters. Loss function, I mentioned it. It cannot be the same one as we used before. So when you're classifying, when you're predicting, when you have a regression model, you're trying to predict a number, you use something like the mean squared error, MSE, or the mean absolute error. One often prefers the former, squared error, because it penalizes the deviations more. You square the error. You could specify it like this, for example, loss equals to MSE. We also have to pick an optimizer, and we use the same one as before. Yes, the Adam. So we actually specified differently from before. Let me just go back to the previous notebook that we have and look for this Adam here. So here we specified optimizer equal to keras.optimizers.adam function. This way we are able to pass in any hyperparameters, so any adjustable parameters of the Adam optimizer. If we don't need to adjust any of those, we can just give the keyword Adam, yes, here. So two different ways of specifying it. Metrics. So what we did before classifying penguins was to plot the progression of the loss during the training. And that's a good first indicator to see, we saw the curve, it dropped rapidly and then it flattened out. But when models become more complicated, the loss function becomes less intuitive, and it can be useful to define custom metrics to show during the training, to observe what's going on. And you can specify that with the metrics keyword to the function. One can specify one or more inside a list. And for example, you could do it like this. You specify metrics equal to taking the root mean squared error function. And there are other options you can pass in here. So now the specification of the model is complete. We have the structure of it with the layers. We have the optimizer, loss function, and the optional metrics thing. So I will just run it here. So let's train it and analyze it a little bit, and then probably soon after that break for the day. There's one difference from before. We will use explicitly a batch size. So this will define how many samples of the training data will be shown to the network in each at once. So the way it works, if I go back here, is that you don't pass a single observation with the different features one by one into the network. You feed multiple ones. And you don't normally feed the entire data set either. You could do that. You could, for the penguins here, you could pass in all whatever 500 observations and train, and that would be one epoch. But normally what you do is to split it up into batches. And a good starting size for the batch is 32 samples, so 32 observations. So larger batches produce better, more accurate gradient estimates, because we really don't go into any theory here, but Hossein mentioned the backpropagation at the beginning, and that algorithm is based on computing the gradient with respect to all of the weights in the network. And you get a better estimate of the gradient if you have bigger batches. But there will also be a less frequent update of the weights if you do this, and it might be less efficient. So a good starting point is to pick something like 32. Otherwise, this looks similar to before. We will run 200 epochs and set a verbosity parameter, how much output we get. So I will now run the training. You see that it's still very fast. And this is what we saw before when we trained on penguins. That's the default output here. We show the loss, we see the loss. It drops quickly. But as I was saying, this can be not as unintuitive of a measure if you get more complicated data sets or models. And this is our custom one that we passed in as a metric. So the root mean squared error, both go down, drop quite nicely. But it remains to be seen, of course, how accurate the model is. It drops down to around 1 here. Just like we did before, we plot the history. So the history was captured here as output, and we can create a data frame with the history from the history object, and then extract the particular column root mean squared error, which was the one we passed in here as a metric. And then we just adjust the appearance of the graph. So how does it look for me? Okay, it's a bit jittery, there's some noise, but it drops very quickly, followed by a more steady decline in the RMSE. Okay, so it's just the root mean squared error. It's a very averaged thing. Let's see in more detail how accurate it is in training and predicting sunshine hours tomorrow. So we evaluate the model. That's the next step. What do? We so these are the predicted values from the training data and the predicted values from the test data. We can compare. And it's useful in this case to use a scatter plot. It's a regression task that we're dealing with. And we can compare the true and the predicted values in a scatter plot. So plots in a 2D. You see how it looks now. So what the type of values will this be now? So Y train predicted is number of hours. So these are floating point numbers. Okay, so the plotting code is more complex than before. This is matplotlib. We create the subplots. We set a particular appearance, a style. We create a scatter plot and set some title and labels, and then another scatter plot. So we're doing this for the training data predicted compared to the truth, the observations. So the actual measured sunshine hours the day after, and the same thing for the test set. So copy paste this here. Okay, so is this what we expected? it looked very promising here. So the error is dropping quickly. This is the test set. No, sorry, the training set. So it looks quite clustered around the diagonal. So there's a very good correspondence between the predicted sunshine hours and the true sunshine hours. But the story is not that clear for the test set. I mean, there is clearly if we would fit the line, it would go something like this, perhaps. But it's definitely not as good as the training set. So this might give us an initial hint or suspicion that the model is overfitting. It's predicting well on the training set, but not so well on the test set. So it could be that it's memorizing some things which make it accurate for the training data, but not so accurate for the test data. Yeah, so maybe one could be surprised. This is better than expected. Predicting sunshine hours is definitely not easy. I mean, weather forecasts sometimes predict no sunshine and you get sunshine all day. But let's now be a little bit more rigorous again and compare numbers. Yeah, so we do this again for the training and the test sets separately. So we can compute the loss and the RMSE, the root mean squared error. And what do we see? We see that for the training set, the root mean squared error is around 1, while for the test set is around 4. So significantly worse. Yeah, it's a classic sign of overfitting. To some extent, the model has memorized aspects of the training data. So fit to various types of noise, for example. You know, it has fit expected randomness, but that randomness will not generalize. So it cannot really generalize beyond the training data it has seen. So overfitting also happens in classical machine learning. If you're familiar with that, so the non-deep flavors of machine learning. And usually that's interpreted to mean that we have, if in classical machine learning, far too many parameters than what the training data justifies. So we don't have enough training data, we have too many parameters, it's an underdetermined problem. And the solution would be to reduce the number of parameters to avoid the overfitting. But it's not exactly the same story in deep learning. Of course, this can be a sign of having that our model is too big, too many parameters, too many layers, too many nodes. But one doesn't really see it always as a drawback to have very many parameters. It can often be quite acceptable to have huge models as long as they perform well. So so one often maybe wants a model which is on the verge of overfitting, but doesn't overfit, it still generalizes. So normally one would attack the problem. There are many different ways to attack the problem before you need to consider reducing the complexity of the model. And we'll see many such techniques, like regularization techniques. We'll come to that. But first, it can be useful to set one's expectations. I mean, this is not a general AI capable of human intelligence. It's a statistical model. So is there some baseline of accuracy that we can compare to maybe make up our minds about whether this is acceptable accuracy or if it's completely useless? So it's a difficult problem to predict the number of sunshine hours. What type of accuracy can we actually expect of a machine learning model, regardless of how complex or optimized it is? So one way to do it for the current case, maybe it's a rather simplistic way of doing it, but it's an interesting comparison. So let's compare our model to the empirical prediction of tomorrow. Tomorrow will have the same number of sunshine hours as today. Sorry. So this is often, it's like an empirical observation. It's quite common for the weather tomorrow to be similar as today. So that's also a prediction. So let's now compare these things. So the baseline prediction is, let's see, we extract the Basel sunshine column from the test set and compare it, the baseline that's the baseline prediction, and we compare it to the test set here. I hope this becomes clear when I plot it. So the true sunshine hours versus the sunshine hours yesterday. This is simply that correlation, and clearly there is a correlation. But how does it compare with our model? It's not easy to see whether this is worse or better than what we see here. This is the trained model. So we can do be a bit more detailed. We can compute the root mean squared error for the neural network, where we pass in the test set and the prediction, and do the same for the baseline. So the test set and the baseline prediction that we just simply picked from the test set. What do I get? Yeah, so I am slightly worse than the baseline. Not much worse. It's similar quality. But obviously, the baseline is a simpler model, so it would be overkill to use a neural network if one can simply have a rule of thumb that tomorrow's weather will be similar to today. So hopefully we can do better than this. So I'm wondering how far to go. I think I will leave the rest for tomorrow. It's 10 minutes past 12. We were a bit generous with the timing in the schedule. If I can find the schedule here, it's until 12:30, but I suggest that we break. I stop here, but I don't need to leave. We can stay here until 12:30. You can play around yourselves and ask any questions you have. And then we finish this episode here tomorrow instead, tomorrow morning. So this is where we left off yesterday. We just compared our prediction. Well, this is actually a graph showing the correlation between the simple prediction of using yesterday's sunshine hours to predict today's sunshine hours and comparing it to the true sunshine hours here. We see that there is a good, well, there is a correlation. It's not good, perhaps. But the question was, is it better than what we get with a neural network? This comparison is relevant because we should always ask ourselves, what accuracy can we hope for? When can we be satisfied with accuracy? How much better than existing approaches does it have to be? And on my machine, I saw that actually the neural network, I got these exact numbers here. Oops, I will go here. I got something like, yeah, the same numbers, I believe. So the neural network is not better than this very simplistic model of using yesterday's sunshine hours. So let's now move on. First of all, we will talk about the validation set. If you remember yesterday, we did a two-step split. If I just scroll up. So we imported the same function as we did in the first part with the penguins, train test split. We split first with a fraction of 70% to 30%, and then we split the 30% into a validation set and a test set, two separate sets. And they cannot be the same. One will be used to monitor the accuracy of the model, and tune hyperparameters to see what works better. And the other one, the test set, is used as a neutral test set, which is not implicitly used in improving the model. So one needs this sort of neutral test set for that purpose. So now, let's see now how we can use explicitly the validation set during the training. What do we want to do? We want to initiate a new model first. And because we had it defined in a function, we can just call the function once more. Because otherwise we would be continuing from where we left off. So then we compile the model with the same optimizer and the loss function as yesterday. And then we add this metric. Or did I already do this yesterday? I don't think so, no. So I hope you found the right place in the episode here, watching the model training closely. Let's see, I will go to the bottom of my notebook. Recreate a model, and we add this additional metric, which will be useful to see during the training. And we run training now for 200 epochs, batch size of 32, and we pass in the validation data. These are the validation data that we extracted in the beginning. We see now that both the loss function, the one we defined for our model, and the root mean squared error of, so both the regular loss function and the loss function for the validation set, as well as the root mean squared error for the model and for the validation set are printed. Maybe if I increase the size of the window. What do we want to compare? So clearly the root mean squared error of the validation set is dropping as well. That's a good sign. It's not dropping as fast. So this is, again, probably a sign of some overfitting. I think we can get a better overview if we plot this. So let's do another line plot. So comparing the root mean squared error for the training data and the validation data. Okay, so it actually doesn't look all that good. So if we only looked at the training data performance, we could become optimistic. It's decreasing rapidly, it's very steady, it's converging perhaps towards a good solution. But the validation data shows us that this is a false hope. There is some overfitting going on. So when the neural network is evaluated on the validation data, the performance is not good. So it has clearly memorized some aspects of the training data here. It's showing good performance because for the wrong reasons, simply. It's a model that does not generalize well. So we want to counteract model overfitting. One way to do this is to create a smaller model. We can redefine the function that creates the neural network by adding two arguments, how many nodes in the two layers. So nodes 1, nodes 2. What happens if we drastically reduce the number of neurons in the layers? 10 and 5 instead of what we had before. I don't remember, 150, I think. So if we were working with classical machine learning, that's probably what we would do, because you don't want to have an overdetermined problem. But the story is not as simple, perhaps, in deep learning. So big models are acceptable. But let's still see what happens. We have drastically reduced the size of the model. It's a small model. It only has 961 parameters. do the same thing as before, compile the model and fit the model. Now there's a lot of copy pasting. Let's now compare it again. Same plot, comparing the, so the main point here is that it's convenient to pass in the validation set because we can use the history from the training. We don't need to make predictions with the model. We can simply extract, the history from the training to see the performance on the validation set. I will make the plot here. Okay, so what do we learn now? It's a smaller model. The overfitting seems to be less severe. The difference between the validation set and the training data is not as large as we saw before compared to here. I mean, this is going seriously wrong. Now it's still not perfect, but the problem is reduced. So reducing the number of parameters can be a strategy to avoid overfitting, but usually that's not the main way to go when we work with deep learning. And one reason is that it can be difficult to find this sweet spot with the number of neurons and the number of layers. And that's also a moving target. So if we would add lots of data, maybe we would want to increase the size of the model again. So that's normally not the approach we use. Instead, we use different types of regularization techniques, and Hossein will talk more about that later. The first approach, which is quite often used, is maybe the most common technique to avoid at least severe overfitting, is early stopping. Very simple. So the model is converging here, or maybe we should look at the big model. The model is converging, but then it starts overfitting. So simply stop somewhere around here, where the performance on the validation set is quite good, and yeah, overfitting is not taking place as much as later. So early stopping. This is, let's see, where are we? Yeah, so first we want to create a big model again with 100 neurons and 50 neurons in the two layers. We go back to a big model, and then we use something already available in Keras. It's one of the callback functions, callbacks, early stopping. So the callbacks are something you can pass into the training for something to happen. It could be to print the performance also on the validation data, or it could be this early stopper that we define here. And there are some arguments, there are some parameters here. So we monitor the validation set loss. That's the quantity that will determine when to stop. And we add a patience parameter because we don't want to stop as soon as the curve starts going up again. We want to average over a certain interval because the curves are noisy. So there's some noise. So there's a window of 10 epochs over which it will average. Does that make sense? Are there any questions? So why does the validation set need to be different from the test set? Good question. So it is because we want a part of the test set should be, so if we only had one test set, we would be using that test set to tune, for example, our hyperparameters. So we would run on the training data and we would get a certain performance, and then we would want to maybe change the number of neurons, or we would add early stopping callback, or we would work with the other hyperparameters of the model and see if it improved the performance on the test set. And maybe we would settle on a given setup, particular selection of the hyperparameters, which gives the best performance on the test set. But then the test set has been used to train the model implicitly, right? It's not neutral anymore. So the training set is used for the automatic machinery going on inside the neural network during training, but you are using yourself the test set to tune the hyperparameters. The validation data set is to have sort of an extra part, so we don't use the test set for both parts, for both tuning the hyperparameters and evaluating the performance of the model, of the final model. So there are good questions here. Hossein, I hope you can have a look in HackMD and answer these questions.
Sure, yeah.
I will have a look later as well. Okay, so let's just try this early stopper thing on the big model. What happens now, as you will probably see, is that it won't go all the way up to 200 epochs. In fact, it stops already after 39. And how does the curves, how do the curves look? Okay, roughly what could be expected, perhaps. It stops early, and there's not a lot of overfitting. But is this really enough? Early stopping is definitely used quite a lot, but there are other methods that we will discuss now. Anything more to say about early stopping? Yeah, we have not really reached an optimum yet. We stopped early before we started overfitting, but there is much more we can do. And this one very common approach, which is very powerful as well, is batch normalization. It's called the standard scaler for deep learning. And how should one explain batch norm? So it's in practice, one adds it as a layer in the network. Batch normalization, we place it here immediately after the input layer. And what it does is to, for each mini batch, which is passed into the network during training, it calculates the mean and the variance of the data points. So it calculates the mean and the variance and optimizes parameters. It shifts. It has, I think, 4 parameters, which are explained further down here. The moving mean, the moving standard deviation, an additional scaling factor, and an offset factor. So it basically normalizes the data coming in batch by batch in order to get better behavior of more, how should one explain it? Hossein, help me out. How would you explain the batch normalization?
Oh, well,
intuitive way.
Yeah, sure. Yeah, I mean, the way, so the way I would describe it is that, so imagine when you have a data, let's imagine a 2-dimensional data, right? So you have X and Y. If you plot it, you might get, let's say, I mean, some sort of distorted circle or, field circle. But with batch normalization, what you do, you center that circle and you make it a perfect circle. So batch normalization helps you to get rid of all of artifacts that each batch of the data has.
Right.
So that's what you do. You get rid of, you just normalize each batch so that the network just sees a regular set of data instead of fluctuation in numbers.
Yeah. Yes.
So this way you get rid of a lot of noise. A network can learn much faster.
Okay, so let's just see how that works in practice. we have early stopping. Let's now import the batch normalization type of layer from Keras. And recreate a network now. We redefine the function. It can be the same function as before, except we add the batch normalization layer. And also, just to highlight or emphasize what Hossein said, traditionally what one has been doing in classical machine learning is to normalize the data before you pass it to the training. And that feels intuitive because you don't want certain features of the data to dominate because it has such large numerical value in those features. So you want the features to be distributed over a similar numerical range. But here this happens inside the network. So that's the difference. This starts to look familiar, I hope. We compose the network and we create it. And we see that there are many features, parameters associated with the batch normalization layer. Specifically, in our case, 356. And that is simply because we have 89 features of each observation from the input layer. So four for each. So 4 times 89 is 356. Those are the 4 parameters. Okay, we fit as before. Again, we have the callback to the early stopper. We pass it the validation data. We check how this works. It stops early and the performance seems to be, there's much less noise. There is overfitting, definitely. There's a difference here. I don't know if my curve looks a bit different from here. I'm not sure what the difference is, but I think
it's fine, Tor. It's absolutely fine. It's all about how how you split it, train and test set, and then
sure.
It's quite arbitrary. You don't know really how that happened.
No, we're approaching the end of my part here, and then there's an exercise for you to do. So, but let's just look at the performance now. The total performance, our predicted sunshine hours. That's just taking now the model and predicting on the test set. The test set we've been holding out this entire time. We've been looking at the performance of the validation set here. And one could now start tuning further hyperparameters and trying to reduce the overfitting even further. And then finally, using this test set that the network has not seen at all so far. But now we do it right away. We have a look at the performance on the test set. Yeah, I mean, it's clearly a linear correlation here, but there is lots of noise. So here's an exercise now, and I suggest we do this. I think it could be useful to do this in breakout rooms. We split up into a few rooms, and Hossein and myself and Ying will jump between the breakout rooms, answer any questions you might have. So this is sort of the point here is to train your muscle memory. Do the whole process again, but with some modifications of already from the beginning. So I don't know if anyone thought about that in the beginning. So we are trying to predict the number of sunshine hours in one city, Basel. But what columns do we have in the data set? We have the weather observations from all the cities, from Stockholm, from, I don't remember, all the cities spread around Europe. And of course, weather is sort of very complex. It has non-local, it has correlations over multiple long length scales and time scales. But maybe we could simplify the model and only look at the observations from Basel. So cutting out all the rests. And instead of using only 3 years, because we're saving some space, we're throwing away many features here, maybe we afford computationally to use a much bigger chunk of the data set, so using 8 or 9 years. So your task will be to do this, use more data and remove all the cities from the training data, which are not from Basel. So you will have to go back to your notebook, scroll up, have a look, and insert this in the right location. And then rerun the last model we had, which included the batch norm. You can recreate the scatter plot and compute the root mean square error. And see if the prediction is now better than what we had before.
So, so far we've learned about condensed layer and a little bit about, I guess, batch normalization, how one can apply it. But these are not the only sort of layers one can use in deep learning, especially if you're dealing with images. As you will see, it's really expensive to use dense layers to use for classification or dealing with images. What we usually use is convolutional networks or convolutional layers. And in this section, we will go through some examples and see how they are being used in real case. So we are dealing with this data set. I don't know how to pronounce it, but let's call it CIFAR 10. It's a data set made of 10 objects. If you go to the website, you can actually read about that these 10 objects are these 10 objects. The good thing about it is already regularized to a specific shape, and it's all already labeled, so makes the life much easier for working with it. So let's just get started. We import TensorFlow. Sorry, it's TF. We check TensorFlow is available. Yeah, I'm using Google Colab, so it's in the cloud. Might be a little bit slower. So what we do now, we want to load the data set. Okay, so data set is loaded. Let's have a look at the images and see, yeah, how they look like. So as you see, we have 50,000 images. So 32 by 32 pixel, and of course 3 RGB channels. And as you can imagine, this is a huge data set. We can't really use, I mean, we can use, but it takes a lot of time for training. So we're gonna choose smaller subset, as you see here. Well, this is going to be an exercise, but I'm going to do it for you to have a better understanding. And I remember there was a discussion yesterday about labels. Okay, labels. Google doesn't want to help. Okay. So okay, yesterday someone asked, can I use, instead of one hot vector, a number, I mean, or a vector? And I said yes, you can use a single number for a label. So what did I mean by that? Let's imagine now you pick. So you see image 1, the label of, which is actually image 2, because in Python everything starts from 0. The label of image 2 or index 1 is 9. So instead of using one hot vector where you have 10 values and a number 10 is 1, you can have just a single number. And as you can see, we will use this, which is called sparse categorical entropy in the language of TensorFlow. Okay, and if I want to just get the value, that's how I do it. Yeah. So you will need these commands soon. Question. Let's pick a data. Let's say one example. The first one. And one channel. Okay. What is the maximum here? And those who have worked with, oh yeah, I haven't imported NumPy, sorry. Import. Yeah. So we know, I mean, when we deal with images, numbers changes between the 0 and 255 in all of the 3 channels, red, green, and blue. So what we usually do, we scale it to 1 because that's much easier to work with when you train a model. And well, I guess with that, we already explored the shape of the training, the images, and the labels. We know we have 3 channels. We know how the number varies. And now what we want to do, we want to, as I mentioned, to change that to make it between 0 and 1. First, let's pick a smaller subset because the main subset is really large. And then what we scale the image to make it between 0 and 1. And well, of course, the class names, I mean, we can read the class names from here. But it's already, I mean, the creator of the lesson has already made the life easier, so I can just copy it from here. And we can actually pick a bunch of them and plot them to see how they look like, or make sure that at least the data set we are dealing with is exactly what it's supposed to be. Yep, looks the same. Okay, good. Now, question, why do we want to deal with convolutional layers? The answer actually it's rather easy. The answer is that if you want to do the same job with fully connected layer or dense layer, you're going to need a lot more neurons. What do I mean by that? So if so I said train images. Let's have a look at the shape. Just that shape. So if I want to use one of these images as one vector, as you know, one big vector, what I have. So I have 32 multiplied by 32 multiplied by 3. It's calculated here. So the number is rather large. So I have a vector made of 3072 numbers. And you can imagine if you create a dense network with such an input, you're gonna, I mean, your network will blow up very fast. And this is what we're gonna do here in this exercise. So let's imagine I have 10 hidden layers, and I want to know how many parameters one hidden layer will need. So I know this is the dimension. So then how many hidden layers do I have? Let's say number of hidden, yeah, right? So, and then I have bias, which is again number of hidden layers. So I will have dimension multiplied by number of hidden layers plus number of hidden layers, true? Yeah. So that's how it's usually done, because we need this number of weights to multiply by dimension, and this is the bias they usually have. yeah, the same thing as you can see. And well, and of course, here they assume, I mean, there's one thing here. Here they assume that you're dealing with one channel. So meaning that you, for example, you transfer your image from RGB to grayscale. Then instead of having 3 channels, you will have just 1 channel. And yet you can see you're going to get a huge number. And actually, if you do it as I did here for 3 channels, the number will be much bigger. So yeah, no, actually, yeah, okay, this is, do they use, yes. Anyway, so imagine now how many, if you have 10 more hidden layers, this just grows quickly. And even the performance is not that good. So that was actually the intuition behind going for different sort of networks, which are convolutional networks. Well, you can also check yourself if you want to create a model and see how many parameters you need. And here it's done for you. And I wanted to just tell something because there are 2 ways to actually create a model in Keras. One is sequential, the other one is functional. And the difference is in sequential model, you always have a feed-forward network, meaning that you have an input, and once this input enters your model, the output of each layer will be the input of the next layer. So this is sequential model, and in the Keras, you have Keras models dot sequential. Models dot sequential. Why it doesn't find it? Sorry, I have to. Model doesn't have attribute. It should be model or model.
Is it not small m?
No, yeah, maybe you're right. I forgot actually. Yes, yeah, true. So you can actually, what you see here, you can do in this way. So if I use Keras dot layers dot input, so I can say shape equals dim, and then the output, all I need to do is to say tf Keras dot layers dot dense, and how many units? Yeah, 100. Yeah, 100, of course, yeah, because that was the number of hidden unit. So I call this model sequential. And if I run this, I should get the same. Yes, as you can see, it's the same. Everything is the same. But what is the difference between a sequential model and a functional model? In the functional model that's written here, or the way also Tor explained, is that you don't need to have a feed-forward network. Sometimes in most networks, because of if the number of layers, when the number of layers increases, then you're going to have this vanishing gradient problem. So you want to have skip layers, you want to have concatenation of the layers, you want to have a lot of things happening between the layers. And that's where you need a functional Keras instead of sequential Keras. But for this course, we can just stick to sequential Keras because it makes life easier. You don't need to think about input and output and some other parameters. So yeah, this was the introduction why we need to have convolutional layer. But what is a convolutional layer and what the convolution does? Convolution is a mathematical kind of calculations that I will just go through it here, and then we will see what does that mean. So what does it mean to convolve? Convolution, in a convolution, you will have a kernel or convolution matrix. For example, here it will be, this 3x3 matrix. So you take a chunk of the picture, you multiply element-wise each one of these, and then you sum it up and you put it inside the corresponding index in the output. So as you can imagine, doing this, your image will shrink. If you check these two sides, you can obviously see that this shrank quite a bit. So this is the convolution. And if you have 3 channels like RGB, you do it for each channel. But what the convolution does, it actually helps you to find features in your picture. Like, for example, this convolution helps you to find edges in your image. So if it's a grayscale image, so obviously when you have 0, that means, I guess, white. When you go towards 100, that means black. So this is an edge, right? And if you convolve it with this filter, you see that the filter already captured the edge right here. So with this convolution, I found edges in the image. And you can see, for example, this very fine gentleman looking through his instrument, his edges were found by applying to this convolution. And when we do the convolutional network, you will have a lot of those kernels that finds a lot of features inside the image, and thereby we can find, we can actually classify or find what is inside the image. And yeah, that's more or less the whole convolution. But how we do it, well, you're going to see in very soon. Let me just go through some of the stuff which are mentioned here. So yeah, I mean, if you, of course, as I mentioned, if you apply, for example, around the border, you will have 2 options. You either can, start from here and you get these, or you can start padding, and then you can keep the size of your image. And that's a choice you can have, but it shouldn't really matter at the end of the day. And interesting, now it's really interesting to do the simple calculations. So now let's imagine I have 3x3 kernel like here, and let's say I have hundreds of such kernels, meaning that I can capture hundreds of features of an image with 3x3 kernel. How many parameters do I have? Very simple, right? Just compare this to the fully connected dense layers we mentioned above. So you can get a lot of information from an image using convolutional networks with way less parameters. So this is going to be our first convolutional network. I'm gonna write it in sequential way as I did before, and we're gonna train this and see how the result will look like. And yes, and I will also explain to you. Oh, sorry, we're gonna train this one, not this one. So, but well, just for the sake of exercise, let's do this model. Call it 0. TF keras dot model sequential. Okay, so I have input layer TF keras dot input. So, I mean, here is one thing to say, that you don't need. You don't need to have input layer. If you don't specify your input layer, what happens is that when you apply the model summary, you're not going to get any information, because Keras doesn't know how your input looks like, so it doesn't know how many parameters you will have. So the reason that we add this is to, to have the output of this command. You can actually check and see yourself during the breakout session. So if I have this, and then I need to have the keras dot layers convolution 2D. So I need to have 32. So yeah, the first number tells the convolutional layer how many pixels does it need, then it's the size of the kernel, and of course, what sort of activation you want to apply after the convolution. So here is a ReLU, but you have other options too. Okay, just to be faithful to this. Then just dot layers flatten tf dot flatten. Oh, sorry, layers dense. So how many output? Yeah, of course, because we have 10 classes, we can't have more than 10 dense layers. So I will, and now I have to explain what I've done here. Okay. So now I have model 0. It should be ready. Okay. Yep.
For the input layer, the shape is a bit off.
Oh, true. Yeah, it does need a shape, and it should be like this. Thank you. Model 0. Okay. There you go. So this is the model. But what we've done, we have taken. Let's say an image or a batch of images. We convolve it 2 times, and I assume yes. So the padding is valid, meaning that it shrinks the images as it goes forward. And you can see in the size, after the first convolution is done, the size went from 32 to 30 and then to 28. And then since I have 3 by 3 channels, the number of channels will, here I have to correct myself. These are the number of channels that you apply, and this is the kernel. When you apply the kernel, the size of input decreases from 32 to 30 and 28. And since the first convolution has 32 channels, you will have 32 channels the second. And the flatten, what the flatten does, because at the end of the day, you will get a bunch of channels in this shape. And you want to make this as a large vector and connect it to the dense layer. This is how a normal convolutional network looks like. Anyway, so yeah, this is the first example of this is a convolutional model. You can actually train it, but you're not going to get interesting result out of this. So to have it a little bit more sophisticated, we can go for larger networks, such as this one. Well, we can do the same thing. We can either do it sequentially or do it functionally. Well, it doesn't really matter what to do, but to make life easier, I'm gonna do it functionally as it's done in the course. But since I didn't import Keras, I need to load it from TensorFlow. You also save your time for my typing mistakes. Okay, now I have to explain to you what is the new layer that I've added here, max pooling. So there's this concept of scaling in images, and in general, if you studied physics, you know that if something is true in one, let's say, if something true in Ising model or any other model in bigger scale, if you zoom up, that still is true, meaning that you can still keep information by scaling up or by reducing pixels or reducing the resolution. And that's what max pooling does. Max pooling pulls out some of the pixels and forget about the rest. And you can see it here. For example, again, you can read more about max pooling, but this is the general feel I'm giving to you, that's what the max pooling does. And the more you do the max pooling, the more you reduce the number of parameters your model will have. And again, what we do here, we convolve with 32 filters or channels, and each channel with this kernel, we max pool from it, and by max pooling, you reduce the input, and you can actually see it here. So by doing this max pooling, 15 by 15, how much the input has been reduced. If I do it 2 times, so I get to this flattened bit, which is much smaller than the previous one, and then one dense layer to the next. And usually you usually have 2 dense layers instead of 1. And these 2 are called fully connected layers. And then, of course, 10 here is the number of classes you have in your data set. In Cypher 10, we have 10, but you might have any other number. Okay, so what we do next, we want to train this model, and we want to train it using the specification given here. So we use Adam as an optimizer. As for the loss, as I mentioned above, since for specifying the label, we have just one number, we have to use sparse categorical entropy. And please pay attention to the next bit, which is from logits true. And this is important because I don't have a max pool, I don't have a soft max after my dense layer, meaning that the output of my model will be unnormalized data. And since it's unnormalized, I do need to tell to the TensorFlow that normalize it first before applying the loss. And you can check, we will check it together. And you see this is important in getting numbers right. Okay, now the model, let's fit it and hope that, yeah, 10 epoch, I guess we should be fine. So since it's learning, let's just have a look at this question, which is a very interesting question. So let's imagine I add, this is the model we have, right? So we have 2 max pooling, 2 convolution. So this question asks us, what if we add one more convolutional layer? So what will happen? Does the number of parameters increases or decreases? Why? So keep in mind that whatever comes out of convolutional layer will be fed to a dense layer. And the number of, and here's the catch, the number of the weights in the dense layer has everything to do with the X, right? Bigger the X, bigger the number of weights in the dense layer. So it's not just, yeah, it's true that it increases the number of parameters, right? But it also decreases the shape of the vector after the flattening. And as you will see, number of the parameters in dense layer is actually the important bit. Yeah, decreased. And it's just because of the dense layer. And it just tells you like how, wasteful is a dense layer, and why we should, when you design an algorithm for your deep learning, why you should think smartly about what you want to do instead of using a lot of dense layers. So let's just now plot what we have, and the result, yeah, should be available. Yes, well, similar, not bad. Accuracy is 60%. Okay. Not acceptable, but not bad.
So the accuracy here, it's defined as the number of correct classifications
Exactly. Yeah.
out of the total.
Yeah.
That's one of the metrics that is used. There are other
Yes.
metrics for the negatives, the false classifications, I think.
Yeah. I mean, this is like out of 10. I mean, if I just take one sample, 60%, I have the chance of getting it right, which is terrible. But I don't have much more expectation from a small network like this. So yeah, I mean, we can actually do this and see if this changes something, which actually, yeah, changes a little bit, increases the accuracy by adding, well, but with the fewer parameters. Maybe that's actually a good example to have a look, because now we added one convolutional layer that has a few thousand parameter less, but is more accurate. Yeah, sorry, I forgot TensorFlow. Yeah. The summary. So as you see, 60,000. This one without the max pooling. 47,000, 10,000 parameters less, 11, almost 11. More accurate. That's the from bit.
So there's they reversed the max pooling and the convolutional layer somewhere.
Oh, yes,
there
here.
only, yeah.
Okay, yes, okay, yeah, that makes sense. Okay, yeah, this is true. Usually after one convolution, you have one max pooling. That's true.
There's a the first max pooling there comes directly after the input. If you scroll up a bit.
Yeah, this one, which is which is nonsense. Yeah, okay.
That should be after the
here.
Exactly.
I mean, this is what we do. We convolve and then we do max pooling.
Yep.
So.
Good catch. Thank you.
Yeah, thanks. Yeah, this is actually has to be referred to incubator.
But take the solution, copy the solution. It's in the correct order there.
Yeah, that's why it's running actually. Okay. Anyway, so yes, I mean, the takeaway is simple. The takeaway is that you can actually get better results, sort of, yeah, because as you will see, we will have overfitting. You can get better result with fewer parameters if you know how to set up your model. Okay, yes, there you go. Actually, you just have accuracy, but let's have a look at loss.
There's a good question in HackMD. Can we do a confusion matrix for this problem? We can, right? It's a classification.
Yes, it's possible to do.
So that's probably a good idea. It's good homework. I don't know if we can venture to try this if we have time at the end of the workshop to construct the confusion matrix.
Yeah, we can do that. But
let's see if time allows.
Yeah, we go through this and we can actually create confusion matrix. True. Well, but the confusion matrix here will be, I mean, 10 by 10, like not something very pleasing to have a look at, but it's possible. So yeah, let's just get to the what we want to do next, which is regularization and overfitting. So as you can see here, the loss function, as I mean, there was a question HackMD, what if we increase number of epochs? So I mean, your network has few or limited number of parameters. There are two possibilities. Either your loss will plateau, best case scenario, and your validation loss also plateau, meaning that there's nothing else that your model can learn from the data set, or you can do the overfitting, as the case here, meaning that the model is picking up some details in your model that's not important or is not the general trend. And how we're gonna kind of deal with this situation. You saw batch normalization, which is a way to deal with fluctuation or irregularities in your data. But the more important way of dealing with overfitting is to use regularization. So there are several ways to apply regularization. The way that we're gonna do in this workshop is dropout. And well, there is one thing that I've seen here, and I do not agree with, is that when you do the dropout, you create multiple paths. Well, that's not actually true. So what regularization does, regularization changes the weight in your network, and I will get to this a little bit in deeper. But let's just have a look at this picture, because this actually gives you what overfitting means. So let's imagine I have this bunch of data, and by the way, this is from a course by Andrew Yang, so all the credit goes to him, but I'm just using his picture to convey a message. So let's imagine I have a bunch of data and I want to classify or find the boundaries between the circles and cross. So if my model doesn't have enough weight or enough parameters, it might find the boundary between these two like a straight line. This is underfitting, i.e. you need to have more parameters. So this is just about right? So you have kind of some outliers, and the boundary should look like this. But if you do overfitting, your model will start picking small details that's not really about the general trend, like this one. This is the overfitting, meaning that there are details in your data that your model is picking up, but they are not really important, and they are not important. They are in the sense that they don't give a general sense of what's going on in the data. So you want to avoid this. How we do it in dropout, let's just again have these two pictures side by side, because that helps us to know what's going on. So let's imagine I have just one layer, and I have one layer, one neuron, right? So, and my activation is ReLU. What happens? If I do that, I should be able to just get the one simple linear function, right? Something like this. So the more I add layers, the more flexibility I will give to the boundary to have shape. But I want to have enough flexibility, not more than enough. With dropout layers, you regularize the weight. You don't let the weight, your weights, I would say, to exponentially grow, and you keep it balanced. It's not about creating paths, it's about balancing the weights. And the way to do it in Keras is by using this simple command, dropout. So in a functional form, you have an input, and you say how many percent of neurons should turn off randomly. And here, for example, you say 20% of them. And you can actually have these dropout layers before, after the convolution, or even here after the dense layer. So let's just do this and see how this changes the result. Sorry, I'm trying to avoid typing all of this because that would take time. And okay. Yep. and we can train the model. Yeah, this. Okay, yes, sorry. So while it's being trained, so let's just see what else do we have. Pretty much that's the end of this section. So let me just summarize what we've done. So in convolutional layer, what you do, you convolve your image with some kernels. What it does, it reduces the size of the image, but it increases the channels. And inside the channel, you will have information encoded about what is inside the image. And deeper is your network, then the more number of convolution you have. At the end of the day, your resulting image will be smaller, given the padding is valid, not the same, and your channels will increase. And actually, that's the way to categorize images, because each image will have a fingerprint, and you can, by labeling correctly your images and the fingerprints, your network learns that, okay, if there is this fingerprint, that means there is a cat. If there's this fingerprint, this means this is a dog, this is a sheep, this is, yeah, I mean, that's how in general the big picture is about. I do not actually expect this network to perform extraordinary. As you see, numbers here is 50% accuracy, like, you know, nothing better than random. But in general, CNNs are very, very successful in image classification. And if you look through many examples available online, you can see how one can use those in more real-world applications. So with that, I guess we are done with this part.